Hello friends. So today we are going to solve few questions, and these questions are from the year 1996, and from the year 1996 there are a total of 4 questions which are we going to solve. So the first question, and here it states that a thin plano-convex lens of focal length f is split into two halves. One of the halves is shifted along the optical axis. The separation between the object and the image plane is 1.8 meter. The magnification of the image formed by one of the half lens is 2. Find the focal length of lens and the separation between the halves. Draw the ray diagram for the image formation. So we are given this basic diagram. We have two halves. Okay. So let us call this as, so this is our first half, and let us call this as second half. Here the important thing is that the position of the object and the position of the object and the position of the image is fixed, and that distance is 1.8 meter. Okay, so it means if we have object, we can draw, okay, let me draw it here only. So if you have object in the downward direction, let us suppose that is given as AB, then this object AB will be acting as object for a first as well as second convex lens. Similarly, the corresponding image will be formed somewhere here on this screen. Okay, and that image will be also for the first as well as the second. So the position of the image as well as the object is fixed with respect to the first lens as well as second lens. So the basic thing here, and it says that only one lens is shifted and another, or only one the half lens is shifted, other half is kept at a, we can say, fixed point. So we can say that plano-convex lens is having two halves, and among these two halves we are given that only one half is shifted along the optic axis. One half is shifted along the optical axis, and let us suppose we assume that the distance through which this one half is shifted is d. Through the distance that is d. So we are going to have d as the distance between the two lenses. So therefore we can say this is our d, distance between the two lenses. And second important part is that the position of the object and image planes are fixed. Object and image planes are fixed. So it means that position of object and image is same for both halves. For both halves. The only thing is that as only one lens half is shifted, so because of that the effective objective and image distance is going to change slightly for each half, and that will result in, you can see, the change in the magnification. So we can write important conclusion from there, that as one lens half is shifted, so because of that the effective object and image distance changes, and changes for each half, and this results in different magnification. Magnifications. So it means the images that will be formed by the first half and second half will be having different size. So we can draw an approximate figure for that, and let us suppose this is our principal axis and we have an object. Let us call this as A and this as B, and we are having, this is our lower half and this is our upper half of the lens, and the distance between the two is, we have marked that this distance is D. So we can draw an approximate figure for that. So for the image, that will be, so the ray of light will be traveling parallel this way, and it will be striking, let us suppose this is our screen on which the image will be formed, and the other part will be coming something like this and resulting in this formation. So it will be going straight and this will be showing a little bit the bend. So this will be, let us suppose we call this as for A2, this is our lens L2, so it will be forming an image of B2. Okay. So this will be our image because of the lens L2, and similarly we can draw for our lens L1 also. So it will be going something like this, and here it will be, so this will be a straight line and coinciding with at this point, and similarly to coming this point. Okay. So this will be our lens L1, and it will be forming an image. This will be A1 and this will be B1. So we can just draw the A1, B1, they will be overlapping each other. So we are having the lens L2 will be forming an image that is our A2, B2, and lens L1 is going to form an image that will be A1, B1. Okay, they are more or less overlapping with each other, and we can say that the magnification of our L1 is on the higher side as compared to our L2, and the distance between this is given as 1.8. that is a fixed one. So let us try to solve it. What will be our magnification and everything? So we say use of the magnification condition for 1/2. Magnification for 1/2, and we are given the magnification of 1/2 is 2. That is given in the question. Okay, and that magnification is given as 2. So we can say this M and is given as 2. Okay, and let us suppose that is the magnification of the half which is unshifted, that's our first half. So we say that for first half which is our unshifted, so for that we can write that our M is equal to V upon U, which will be coming as 2. So we can say that our V will be equal to twice of U, and let us assume that this U is our X. So we can say let U is our X, but because the object is lying on the left, so this will be coming as minus of X, and this gives us that our V will be equal to plus of 2x, and the total distance from the object to the image that is fixed, that is our 1.8. So we can write that total distance from object to image is 1.8, that is our fixed. So therefore we can write that our U plus V will be equal to 1.8. So this gives us X plus 2x, because we are only interested in the actual distance, so we can take their modulus will be equal to 1.8, and this gives us that our X is equal to 0.6 meters. So it means the distance of the you can say the object from the lens is our X, which is our 0.6 meter, and therefore the image, so we can write that our U now will be equal to 0.6 meters, and our V will be equal to plus 1.2 meters. So we can just plot it on the, so we get U is equal to 0.6, so this distance will be our 0.6, and the other distance of the image that is formed because of this is our 1.2, and this is because of our L1, okay, which is our unshifted. The shifted is our L2. You can say this is our shifted. Now we can use, or we can say we can find out its focal length also by using the standard formula. We can say that focal length one upon f is equal to 1 upon v minus 1 upon u. So this is 1 upon 1 2 minus of 1 upon minus 0.6. This gives us 1 upon 1 2 plus 0.6 and giving us that the focal length will be equal to 0.4 meters, and this is for our L1. So therefore we can also mark our F1 that this will be the focal length and will be coming as that is our 0.4. Next we can find out, now we come to the second half, that is our shifted one. So you can say that for second half, that is a shifted lens, and that is our L1. That is our L2. Shifted one is our L2. Okay. So therefore the object distance will be equal to, that is our U2, and that will equal to minus 0.6 plus D. So we can draw for this approximate here, and this is our object, that is our AB, and we have the lens, and this is our second lens. The distance between the two is given as D, and the distance of the object from this is our L1 and this is our L2. So this we just found out is our 0.6. Distance is D. So this distance of the object comes as D plus 0.6. And now we can find out also for the, you can say, image. The image is being formed somewhere here, and we know that the distance of the image from L1, this entire distance is our 1.2 meters. So because of this L2, this distance will be equal to 1.2 minus D. So we can write the image distance if that is our V2, we can write this as 1.2 minus of D, because both images are being formed here. So this is our A1 as well as A2, and giving us this is B1 and this is our B2. So images are coinciding with each other because they are fixed, only the magnification will be different. So therefore, okay, and the focal length of both the lenses is our 0.4. So we can also draw the distance of the second one will be about 0.4, and this will be our distance of, that is the focal length for the, because both the lenses are same, only difference is that, okay, one second, here I drew it wrong, this has to be with respect to the lens. So this will be 0.4. focal length of the lens, and here also 0.4. So we can just modify it, and so the focal length for this one is here, and this is approximately here, which we already know. So this is our 0.4, and this will be also our 0.4. So we can this will be our 0.4, that's our focal length. And so once again we can use the formula, and we can say 1 upon f is equal to 1 upon v2 minus 1 upon u2. So this gives us 1 upon f is equal to 1 upon 1.2 minus d, and minus of this will be coming as plus 0.6 plus d. Okay. And we already know that our f is 0.4. You can say our f is 0.4. So we substitute it, we get this as 1 upon 0.4 will be equal to 1.2 minus d plus 0.6 plus d. And we can solve it for d, and that d will be coming equal to 0.6 meters. So this is the distance between the, you can say, two halves. Now we can find out the magnification of both the halves. Magnification of both halves. So we can write our first half will be m1, and that will equal to v upon u. So we get this as 1.2 divided by minus 0.6, giving us minus of 2. And then we can find out for the second half, and for second half we are going to get our m2, that will be v2 upon u2. So we get 1.2 minus d, which was 0.6, and this is minus of 0.6 plus 0.6, and this comes close to minus 1/2. So in this, because image will be formed at the same distance, but the only difference will be in their size, the magnification, and they will be inverted because of the negative sign. So we can say that image will be inverted and of different magnification, of different sizes, which we can say magnified, or we can say also say it demagnified. So I think these were the only thing which were asked in this particular question. Yeah, find the focal length and the separation between the both halves. Okay, so we come to the next question, and in this question it was asked in the year 1996, and it states that the angular width of central maximum in the Fraunhofer diffraction pattern of a slit is measured. The slit is illuminated by light of wavelength 6000 angstrom when the slit is illuminated by the light of another wavelength, the angular width decreases by 30%. Calculate the wavelength of this light. The same decrease in the angular width of the central maximum is obtained when the original apparatus is immersed in the liquid. Find the refractive index of the liquid. So this entire question is based on two parts. In the first part, when we change the wavelength, or we can say when we use the another light to illuminate the slit, we get a reduction of the illumination by 30%. And this is same reduction in the 30%, or we can say angular width is decreased by 30%, and same reduction is observed when the entire apparatus is put inside the liquid, and we have to find out the refractive index of the liquid. Okay. So we already know the basic formula for angular width. You can say for angular width is equal to theta, and that will be equal to 2 lambda divided by a. Okay. And here a is the width of the slit, lambda is the wavelength. Okay. You can say a is width of slit, and this width of slit is constant for both cases. Only thing that is changed is the wavelength. We are using different sources, so this is constant for both cases. And it says that angular width had decreased by 30%. So it says angular width decrease by 30%. Therefore, new angular width, if we represent it as theta 2, will be equal to 0.7 times theta 1. Now we can find out the you can say new wavelength, that is our lambda 2. And from here we can also say that if a is constant, then we can write that our theta is proportional to lambda. And we can say that new wavelength let us suppose that is our lambda 2. So we can write the formula theta 2 upon theta 1 is equal to lambda 2 upon lambda 1. And the ratio of theta 1 and theta 2 is nothing but our 0.7. So this is theta 2, theta 1 is equal to 0.7. So this gives us 0.7 is equal to lambda 2. Lambda 1 is our 6000 angstrom. So this gives us our lambda 2 will be equal to 4200 angstrom. So this is the wavelength, new wavelength. Now it says that it is immersed in the liquid. So we can say immersed in a liquid. Therefore, the effective wavelength, let us suppose the lambda prime, will be equal to lambda divided by mu. Therefore, we can write our angular displacement, that is our theta prime, is equal to 2 lambda prime divided by a. Substituting value of lambda prime, we get this as this will be 2 into lambda divided by mu. And this, it says that and we have that is our 0.7. So we can write this as here I missed A. So therefore we can write that our theta prime will be equal to 1 upon mu multiplied by theta. So therefore we can write that 1 upon mu is equal to our 0.7, and this gives us that refractive index will be close to 1.43. These were the two things which were asked in this particular question. Now we come to the next question, and it states that in a double slit apparatus is immersed in liquid of refractive index 1.33. It has a slit separation of 1 mm and distance between the plane of slits and the screen is 1.3 meters. The slits are illuminated by a parallel beam of light whose wavelength in the air is 6300 angstrom. So we have two questions based on this. First one is to calculate the fringe width, and second one is one of the slits of the apparatus is covered by a thin glass sheet of refractive index 1.53. Find the smallest thickness of the sheet to bring the adjacent minimum on the axis. So first of all, we are going to find out the fringe width, and we already know its formula. So we can say fringe width, that is our W, is equal to lambda capital D divided by small d, where capital D is the distance between the slit and screen and small d is the distance between the slits. Lambda is the wavelength. So we can say lambda is our wavelength, and we have this capital D is our distance between the slits and the screen. Distance between slits and screen, and the small d is the distance between the slits. Distance between the slits, and we are given the wavelength that is given in the air. So first of all, we have to find out what will be the wavelength in the liquid. So you can say lambda liquid will be equal to lambda air and divided by the refractive index. Lambda air is our 6300 angstrom, 10 to the power minus 10, and mu is given as 1.33. So this will be coming as 4.7 into 10 to the power minus 7 meters. So this is the wavelength in the liquid. So now we can use the fringe width formula. So we get W, that's the width, will be equal to, this is our 4.7, 10 to the power minus 7, and we have 1.33 and divided by 1 into 10 to the power minus 3. So this comes approximately as 0.63 millimeter. Okay. And we have to find out, I think this was the only thing required. We have to come to the B part now, and in part B we have to adjust the minimum, that is our first order minimum, on the central axis by inserting a thin glass sheet. Okay. So it basically means we have to create a path difference of lambda by 2 between the light waves from the two widths. So we can say that the optical path difference introduced by the glass in the liquid medium. In the liquid medium, and that is represented as delta of x. Then this delta of x will be equal to, we have this as refractive index of glass divided by refractive index of liquid minus 1, and this whole term multiplied by T, where T is the thickness of the sheet. Okay. And we substitute the values, and we can say that okay, and another thing, that this path difference should be also equal to lambda by 2. So you can say our delta x should be equal to that the wavelength that is of liquid and divide by 2. So if you merge these two equations and substitute the respective formulas values, we get this as 1.53 minus 1, sorry, not minus 1, 1.53 divided by 1.33 minus 1 multiplied by T is equal to, we have this as 4.74 10 to the power minus 7 divided by 2. And if you solve it, we are going to get T that will be equal to 1.58 micrometer. So this is our thickness of the sheet that was asked for. And we come to the next question. A right angle prism having angle 45 degree, these are not negative signs, 90 degree and 45 of refractive index n, has a plane of refractive index n1 symmetric to its diagonal face. The assembly is in air. The ray is incident on AB. There are two parts on it. First states that calculate the angle of incident AB for which the ray strikes the diagonal face at a critical angle. And part B, it states that assuming n is equal to 1.352, calculate the angle of incident at AB for which the refracted ray passes through the diagonal face undeviated. So this is the figure. We have a right angle triangle ABC, and there is a plane which is refractive is n1, which is placed on the its diagonal part. Okay. And n is the refractive index of the other face, that is of ABC looking from front, and the ray is incident on the side AB. So for the first part, it wants we have to find out the critical angle. So critical angle is means that we have to use the concept of, you can say, it will be somewhat related to the total internal reflection. So we can just draw the figure for that. We have a right angle triangle. This is our A, B and C, and here on the diagonal face we have a sheet, and its refractive index is given as n1. The face ABC is having a refractive index of n, and to the normal we have a light that is incident this direction. Let us suppose the angle of incident it is making is our I, and so light will be traveling from air inside the refractive index, so it will try to bend towards the normal and striking the face AC. And here, suppose this is somewhat normal, and it will try to go for the critical angle. So let us suppose it just moves along the AC. Okay. So this will be our path of the ray, and you can see this is our refractive angle, that is R, and let us call this as point as M, and this point is N, and we can call this as point as P. And these two angles are of 45 degrees. So this is also 45 and this is also 45. These are the refractive indexes. Okay. So we can use for the critical angle, we can use the, you can say first of all we are going to find out the, we are going to use the Snell's law at point M. So say that Snell's law at M, and we can say this as refractive index of air sine of I, and we have a refractive index of the triangle, that is of ABC, which is given as N. So this will be for N, and this we have sine of R. Mu of air is 1, so we can write this as sine of I is equal to N times sine of R. We will use this expression later on, but first of all we are going to try to find out what will be the various angles of this particular thing. We have to find out the relationship. Okay, so let us consider a triangle AMP, and let me draw the rough approximation for it. So this is our A, and we have this as B, and this will be one normal, and we are going to have this is of incident and this will be our refracted. So we are going to have angle, this angle as R, and this angle will be 90 degree. So therefore this will be our 90 minus R. Okay. And suppose this is C somewhere, not exact to a figure, but it will be something like this, and this angle is given to us 45 degree. So we can say this point is our M and this point is our P. So we can use in triangle AMP, triangle sum is 180 degree. So we can write this as one second. Yeah, so we can say that our angle AMP will be equal to, total angle is our 180 and this comes as minus, one second, is it correct? Okay, we have 90 degree, this angle will be 90 degree, then it is going to go there. So we are going to have this as 90, and we can write this as, let me phrase it again. So we can say angle 90 minus R, so we can say in triangle AMP we have angle 90 minus R, and another angle will be about plus 90, and we have minus of C, that is a critical angle, and plus of 45 is equal to 180 degree. So this gives us that our R plus C will be equal to, this will be coming as 90, 90, 180. So these two terms cancel out. This will be 45. So this will be R plus C is equal to 45. And this gives us that our R is equal to 45 minus C. And if the ray has to go a total internal reflection, we can say if ray just undergoes total internal reflection, the angle of incident of AC at AC, sorry, not of AC, the angle of incident at AC must be critical angle, must be critical angle. Therefore, we can write that C will be our C critical, and which gives us that our sine of C will be equal to N1 upon N. Now, we just formed an equation, and that equation is our R is equal to 45 minus C. So we can write this as sine of R is equal to sine of 45 minus C. And we can just open it, and sine of 45 minus C, we can write this as our sine of R is equal to, this will be coming as sine of 45 cos of C minus cos of 45, and we have this as sine of C. And cos of 45 and sine of 45, they are going to have both same value, that is 1 upon square root of 2, which we can take common. So this will be left as cos of C minus sine of C. And sine of C is, we know, is our N1 upon N. So we can find out a cos of C. So we can write our cos of C will be equal to 1 minus sine square C and its square root, giving us 1 minus, we have this as N1 square upon N square and its square root. So this will be equal to our N square minus Ni square square root divided by N. So we substitute and we get this as sine of I so this gives us that sine of I is equal to N times 1 upon square root of 2, and this will be our N square minus Ni square square root divided by N minus Ni upon N. And here this N cancels out throughout, so we get this as I will be equal to sine inverse of 1 by 2, and here we have square root of N square minus Ni square and minus of Ni, and this is our angle of incidence that was our supposed to find out. Okay. Yeah, and I forgot to mention here this, yeah, let us call this as equation number 1. And we have, let us call this as this entire thing as equation number 2. So here, using equation 1 and equation 2. So from there we are going to get this particular relationship. So this was the first part, and in the second part it wants that the refracted ray should be perpendicular to the face AC. So we can draw an approximate figure for that. And this is our A, we have B, this is C, and once again we have perpendicular, and this is our ray, and it should be going straight from this and giving us a 90 degree. Okay, and let us call this as point as P prime, and let us call this as M. The angle of incident is, let us suppose, I prime, and we have this as N, and this will be over N1, the refractive indexes. So the ray should be passing through face AC and deviated. We can write that for ray to pass undeviated through AC, it must strike AC perpendicular. Okay. So it means the angle of incident at AC should be equal to 0. Therefore we can say that angle of incidence at AC should be equal to 0. Okay. Therefore, if angle of incident at AC is equal to 0, so we can also say the angle of refraction should be equal to 0. Okay. So therefore, at diagonal face, the R prime should be also equal to 0. Okay. But we can write that the angle R and R prime, R plus R prime rather, R plus R prime should be equal to angle A, which gives us that our R prime is 0. So this comes R plus 0 is equal to 45, giving us R will be equal to 45. So this angle is our R, because we simply know that exterior angle of a triangle is equal to sum of the opposite two angles. Simply we can just solve it in that way also. So we were having this as 45. So this is 45. So obviously we are going to get this angle will be also 45, more or less. Now we can use Snell's law. Snell's law, we get our sine of I is equal to N sine of R, and which is our N sine of 45 degree, and this gives us N upon square root of 2. And for n we are already given as 1.352, so we can write this as sine of I, and this Snell's law we are using at m. Snell's law at m. So sine of I will be equal to 1.352 divided by square root of 2. So this gives us that our I is approximately equal to 72.94. So I think this was only second part that was asked. Yeah. So these were the questions which was asked in the year 1996. Yeah, 1996. So this completes all the questions. Thank you.